Our next problem kind of integrates stuff that we've already learned about with the fact that this is chemistry and we're talking about atoms and electrons. And so the idea is that electrons are in orbits around the nucleus of an atom, or in orbitals, I should say, and when they absorb light, they can be promoted or excited to a different energy level. And these energy levels are quantized, which really means they're at discrete energy levels. So you can think about this, if you want to, as a staircase. But what's unique about it is that it's a staircase where the steps are not equal. And so I've got a great little image here on this problem here, that if we're looking at, for example, the ground state here that we have right here, where n equals 1, our ground level, it's a huge step to get to our next step, step 2, and then a smaller step to get to our third step, and so forth. So imagine we're standing, at the bottom of a staircase, but it's a staircase where the first step is huge, the next step is significantly smaller, and significantly smaller after that. But what we need to do is think about how much energy do we need to give that electron to get it to jump from that ground level up to the next level? Or what if we wanted to go from the ground level to 3 steps up? What energy level would you need for that? Because what happens is you will absorb light energy of a certain wavelength that matches that energy gap, and then you'll jump up. Similarly, if energy is emitted as electrons kind of jump back down, because we know the gap in those steps, we can actually determine the wavelength of light that will be emitted. And so the wavelength of light that's emitted for different atoms is not seen as a spectrum of colors. It's really seen as discrete colors, because each of those colors corresponds to a certain wavelength of light. That wavelength of light corresponds to a certain energy. And that energy, again, deals with the height of that gap between different energy levels. And so this is an equation that we can utilize to talk about the differences between these energies. So these n's represent what step you're at, 1, 2, 3, or 4. And so again, final minus initial, that's something that we consistently see. And we're actually going to see these as a inverse square relationship. So we'll apply this in a minute, but you just need to know, all right, when I'm talking about energy in gaps between electrons jumping between levels, this is the equation that we're going to use when we're talking about the hydrogen atom. And in general chemistry, we don't talk about anything except the hydrogen atom, so this is the only one we'll really need to worry about. Okay, so this problem tells us, again, hydrogen atom, that's the only one we're going to deal with here. It absorbs a photon of UV light, and its electron goes from the n equals 1 to the n equals 4 level. So we want to calculate the change in energy of the atom. So we want to calculate the energy difference when we put in that photon of UV light, and then the wavelength of light to correspond for that. All right, so again, we first need to figure out how much energy is contained in that step up that we go to go from n equals 1 to n equals 4. So again, information that we know an electron goes from n equals 1 to n equals 4. So we go from n equals 1 here up to n equals 4. And we want to know what's the height of that energy difference. So we can use this equation to calculate that. So delta E equals RH for the Rydberg constant for the hydrogen atom. So RH times 1 over the final energy level minus the initial energy level. And you'll notice here that this is going to end up being a positive or a negative value depending on whether we're putting energy in to jump up, in which delta E will be positive, or if our electron is jumping down, delta E will be negative because that's energy that's given off. Okay, so in this case, NF is going to be equal to 4, and I equals 1. So initially we start out at n equals 1. We move up to energy level 4. And so when we put this into our problem here, the Rydberg constant for the hydrogen atom is minus 2.18 times 10 to the minus 18th joules. And then we're going to multiply by the difference of 1 over 4 squared minus 1 over 1 squared. Okay. And again, we can already see this is 1/16 minus 1. We're going to end up with a negative value. So this, again, is a negative value. We can already see that. We don't know the magnitude of it, but we can tell it's going to be negative. and multiplied by the negative here that comes from the Rydberg constant, we can see that we're going to end up with a positive value for delta E, which makes sense. We already knew that we were putting energy in. You need to put energy in to jump up in energy level. So solve for this mathematically, we get 2.04 times 10 to the minus 18th joules. So now we know the amount of energy that it takes to jump this gap. What we'd like to do is convert that into a wavelength of light. So again, we can use this equation that we had from the previous problems. And again, I'm going to use the second version of it because we want to solve for the wavelength. That's our unknown. So again, we can solve this equation. Wavelength is going to be equal to hc over delta E. Got to check our units here. Planck's constant is going to be 6.626 times 10 to the minus 34th joules times second. Speed of light is 3 times 10 to the 8th meters per second. And then we just calculated in joules our energy gap, which is 2.04 times 10 to the minus 18th joules. Go ahead and solve for your lambda, and again, we're going to get this in units of meters. It's 9.74 times 10 to the minus 8th meters. But again, to put this into perspective, we're going to convert this into nanometers by multiplying by 10 to the 9th, and we get 97.4 nanometers. And just as a confirmation, right, if we think about wavelengths of light, and we think about kind of the visible spectrum runs from 400 to about 700 or 750 nanometers, and so the ultraviolet is kind of less than 400 in the 100, 50 to 400 range, and so this is definitely within the region that we'd expect for UV light. And since they told us that we absorbed a photon of UV light, that's kind of an internal check that we got the right answer.